Okay, I think that we're gonna just make a start at this time. And let me share my screen. I have prepared a little bit of a presentation for us to use. So, as always, this is going to be our live optional, live online session for this course. Even though this is an asynchronous course where you'll be working independently at your own pace each week, I do want to offer these times and spaces for those of you who feel that it's beneficial to get together and have these discussions a little bit more in a traditional classroom setting. And this week really marks our final week when we're doing these kind of introductory kind of topics. So we've spent some time getting our bases all to the same place, so we have the same understanding as we're embarking on that journey of looking at the human anatomy and physiology one system by system. So this week we'll wrap up this kind of a review portion of the course. We'll talk about some basic chemistry behind the life. We'll talk about cells, and we might even look at the genes a little bit. I do want to emphasize that the full learning material is available for you on the Canvas course. So what I normally do during these live online sessions is that I let it go wherever students want to go and what they want to spend the time talking about. And if I don't have students showing up, I still record these. And I provide it as a rather kind of a nutshell version of the key highlights of the content that we're looking at that week. So the full experience is on Canvas with the full-length lecture videos available for you. What we're going to do today, I really think that we have quite a lot to look at as we're tackling the chapters 2, 3, and 4. So I think that majority of our time is dedicated for that review. If we have time, we'll have a look of the homework for the week as well. Like I said, I normally would be checking in with my students, but since it's just me here today, we're just going to dive into right to the material. And what we're going to see is that really understanding the basic chemistry is crucial for us in understanding how life works. So really, we want to capture the science behind how and what materials are made of, what the structures that we see on those are, how that affects the properties of materials and the behaviors of those materials in relation to other materials and what kind of reactions can take place. So this is really looking at the life in the smallest scale, if you remember that review of the study of the life in various different scales. And we're going to start by talking about elements. So elements are the smallest form of matter that we can break down with traditional means in traditional chemical means in a lab setting. We can actually go beyond elements. We can start looking at subatomic particles, but that requires additional effort and additional tools and methods. So we're going to stick to the level of elements. And what we are seeing here is that really, even though we have so many different kinds of elements, there's really about 4 of those that I want to highlight at this point, because those 4 together represent 96% of all the elements that we find in living organisms. So carbon and hydrogen are going to be really important. They are the backbone of the organic chemistry, and then nitrogen and oxygen as well. We will end up seeing that, of course, there are other elements that are found in lesser quantities in living organisms. And that doesn't mean that they are any less important. Sometimes it's the smallest of amounts that you need, but if you don't have those amounts, we have significant issues. So although we're emphasizing these 4, carbon, hydrogen, nitrogen, and oxygen, it by no means means that the other elements would not be important. So let's talk a little bit about the concept of matter. So anything that has a mass and takes up space in the universe is considered as being matter. So for example, this pen in my hand, it has a mass, And now I want to clarify the difference between mass and weight. Mass is constant, whereas weight is always relative to the gravity. So the weight of this pen will be very different here on the Earth than it would be on the moon, but mass is constant. And what I mean by the pen also taking up space is that it has a volume. We can quantify that, we could measure that. So anything that has a mass or takes up space is considered as matter. And we're going to be starting to kind of work our way through the material by considering different matters. And obviously matter can take different forms. We can have matter in a solid state, in a liquid state, in a gaseous state. And some elements also allow us to have matter in a kind of a fourth state. We wouldn't see that, and that fourth state is known as plasma. We wouldn't see that with all of the elements. So for example, water, which is an example that we often use, obviously we don't see water in a plasma state, but it is available for certain elements. So elements are pure substances, and like I mentioned, we can't really break them down further by traditional chemical means. And they're really the fundamental building blocks of all matter. And we have beautiful work that others have done for us before us of classifying all the elements that can be found and organizing them in a periodic table of elements. And we'll unpack what the periodic table of elements tells us and what's the meaning of that. So the periodic table of elements is a visual way of arranging all these known elements, and they're arranged in a very particular manner. So this organization of the elements on this periodic table of elements is going to give us a clue where these different elements fall in terms of their reactivity, for example, on the considerations that we might have in interactions of materials. So we can organize these elements based on the atom number, electron configuration, and also based on their chemical properties. So often really looking at the periodic table of elements already gives us a good clue of what's going to happen in various different chemical reactions. So for our purposes, we can consider most elements as being equal or being analogous of atoms. And atoms are really the smallest unit of ordinary matter. And atoms are responsible for forming these chemical elements. Often we see that atoms join together forming molecules. And it's really what we want to pay attention is that what are the interactions that we see when we're talking about the atoms. So first thing that we need to do, we need to unpack a little bit about the atom's structure. And many of you, I believe, will have seen a diagram that looks something like this. So here we're seeing a single atom. We see that at the center of the atom, we have a nucleus. And within the nucleus, we will find protons that are positively charged and neutrons that do not carry any charge. And then circling the nucleus of an atom, we will see electrons. These electrons circle around the nucleus on their own plane. And obviously these diagrams that we're seeing are oversimplifications. These electrons are constantly moving on their plane. So this is almost like just a snapshot of one moment in time. But what's important for us to notice is that electrons carry a negative charge, and we're going to be paying attention to the number of electrons and number of protons as we are discussing about some of the interactions that we might end up seeing. So let's have a look of the one element from our periodic table of element, and what we're seeing here, we'll be able to tell a few things from what's listed. First thing that we're going to be able to tell is the atomic number of that element and also the atomic mass of the element. And obviously we have the atomic symbol. So let's unpack those a little bit. So what we end up noticing is that electrons, which were carrying those negative charges circling around the center of an atom, actually have a very, very small mass. So they're not going to contribute significantly. So when we're counting the atomic mass of a element, we're really focusing on the protons and neutrons. And you remember protons were positively charged particles and neutrons were those neutral particles, both found within the nucleus of an atom. So the atom's mass, which gives us the mass number for that atom, is calculated by adding together the protons and neutrons. The contribution of electrons is going to be so insignificant that we can ignore it for our purposes. And there, what I wanted to talk a little bit about is that we do end up seeing sometimes different number of neutrons in the atom. The proton number remains the same, and this will give us different isotopes of a particular element. And these different isotopes are going to be useful for us for a few different purposes. And what I wanted to do next is talk about radioisotopes, which is what my students often think about when we're talking about isotopes. So these are radioactive isotopes of an element, and what we end up doing is that we can use radioactivity both for good and bad things. Some of the things that we do by measuring radioisotopes of the materials is, for example, for determining the age of organic materials. In my former life, I've worked in restoration and conservation in archaeological fields. So what we end up doing is we define the age of a material or age of an object based on the radioisotopes that we can measure. We can also use radioisotopes in medical applications when it comes, for example, for using them as a contrast agent, tracing where the blood goes, where there's activity going on, for example, in a nervous system, so we can show what are the active parts of the brain, and through that kind of figure out more of the functionality with medical imaging techniques. So there's a lot of good that we can do by harnessing this knowledge that we have gathered about radioisotopes. But there is also bad things that have been done. You've also heard about, for example, nuclear weapons and so on. But leaving that behind, I want to talk a little more about this periodic table of elements that we saw earlier on, which really arranged all of the known elements in a very specific manner for us. So we'll see that these horizontal rows are known in periodic table of elements as groups, and these columns are known as periods. And where an element falls in terms of its period and group in this table gives us a way to predict the reactivity of that element, for example. So really, really important information in that sense. I also wanted to talk a little bit about molecules. So molecules are what happens when we have two or more atoms that come together. And as they come together, they typically end up forming an electrically neutral creation, electrically neutral molecule when everything is put together. But what's going to be important when we're looking at molecules and studying of them is really that these different atoms in a molecule are held together by various different kinds of chemical bonds. So we ought to understand those a little bit. And let's start by unpacking this by reminding ourselves that in an atom, we typically, if it's an electrically neutral atom, have the same number of electrons and protons. So we would have same number of negative charges as we have positive charges. And this would make this particular atom, this particular element that we're studying, an electrically neutral atom. What we are seeing is that sometimes when we're looking at this formation of molecules, there might be multiple shells of electrons that we find around the nucleus of an atom. There is a particular rule of how these electrons organize. And the first electron shell that we can have can hold a maximum of 2 electrons when it's full. The second shell has potential to hold up to 8 more electrons on that. And then we can go further and further of these electron shells. And what atoms always try to do, they fill the innermost shell and then move to the next shell and move to the next shell. So that's going to be a key when we're unpacking these interactions. So we are always aiming to reach that stage where we have atoms are actively searching for that stage where they have a full valence shell. What it means that it's a full valence shell is that the outermost shell of that atom has a full amount of electrons, the maximum amount of electrons that can fit into that shell. So that's why it's important for us to know really what's going on with the outermost. We don't often worry about the innermost or subsequent shells. We just focus on the outermost ones, and often we don't even draw out the other electron shells. Sometimes we have atoms where they do not have a full electron shell. And if they're just short of gaining a full electron shell, so they either need to gain one or two or few electrons, or they just need to get rid of one or two or few electrons, they are going to be very reactive atoms. Those types of elements are actively seeking to engage into chemical reactions, because remember, we always wanted that full valence shell. So in this picture that you're seeing on the screen, this would definitely be an atom that would be very, very reactive. It would be easy to do chemical reactions with that. Here's another example that we saw kind of touched upon earlier on. If we just need to get rid of one or few electrons, these atoms also are going to be very reactive. So that's going to give us a reminder that what these atoms are searching for is for the stable state where they have, again, that full valence shell. So now when we look at, based on this information, our periodic table of elements, we can actually figure out something rather neat. We end up seeing that at the ends, both ends, we have more reactive substances, and all the way to the right, we have very stable substances. So when we're looking where an element falls on this table, we can tell, is it likely to engage into chemical reactions? Like, for example, we see that hydrogen is very active, whereas we have some elements that are very stable, so it's hard to get them to engage in chemical reactions. So lots of useful information for us from simply studying the chemistry of life. So now that brings us to looking at chemical reactions. And these are really the processes where we're really trying to rearrange the elements that form a molecule so that every compartment or every part of the molecule would reach that happy state. On the diagram below, you, for example, would see a picture of an atom that has one electron on its third electron shell. So if it's able to get rid of that, it's going to reach that at full valence shell state, because now if it gets rid of that one electron, the outermost shell will have a full number of electrons, and it's going to become a very stable element. Obviously, this could work in another way, that we have an atom that has almost full electron shell, and it's simply trying to gain one more electron to get to that place. So this is really what tells us what's reactive, what's not reactive. And when we are looking at chemical reactions, this is often what we're working with. So we're looking at what's the original substances going into the reaction. These would be known in our proper scientific language as reactants. So reactant is what goes into the chemical reaction, and what comes out of the chemical reaction is going to be our product. And here we're seeing just this very simple chemical reaction that contains one atom. But often we would have multiple elements, and we would quantify the amounts and balance our equations and so on. But we're seeing we have our reactants, what goes in, then we have the reaction, and then we have what comes out of the reaction, which is going to be our products. So useful terms to know for later. So like I said, this can get a little bit more nuanced when we have multiple elements that form a molecule. So for example, here we see two hydrogen atoms and one oxygen atom. Well, these would be the reactants of the chemical reaction that we're looking at. the chemical reaction takes place, and as a result of that chemical reaction, we're now forming a molecule where these two hydrogens and one oxygen molecule have joined together, forming a water molecule. And the output of the chemical reaction would be our product. Similarly, we can see that we don't always just build up new products. Sometimes our reactant can be a larger molecule, and it gets broken down into multiple products. So it's not always making from small particles to something bigger. It could work the other way around. And we have two different kinds of reactions, chemical reactions that can take place. Sometimes these reactions are what we know as irreversible reactions. And by that we mean that the reaction moves to one direction and one direction only. So in a room setting, if you leave a container of hydrogen peroxide out, over time it will turn into water and oxygen. So that is a one-way reaction. That's the direction where the reaction will be going. Sometimes we also have reactions that are reversible reactions, so they can go back and forth between different states. So we can have our reactants, which would be, in this example, our bicarbonate molecule and a hydrogen. And if those choose to join together, we form a carbonic acid molecule. So the reactants were bicarbonate and hydrogen, and the product is going to be bicarbonic acid. But this could work the other way around. We can convert bicarbonic acid or carbonic acid into bicarbonate and hydrogen. So in this case now, when we're moving from the right to the left, the reactant would be our carbonic acid and the products would be our bicarbonate and hydrogen. Sometimes these reactions get much more complex, so there's multiple steps, and this is really where the chemistry becomes interesting and becomes more complex. So we have chances to alter with each of these steps and see what happens. So let's have a look of these bonds that we end up forming. Like I said, when we are forming molecules, when individual atoms to come together, they are joining to other atoms and bonds form. So covalent bonds are when atoms that form a molecule end up sharing electrons. So this is very much sharing is caring kind of a setting. Everyone that's part of this forming this molecule, all of those elements actually get that happy place that they want of having a full valence shell. And how they get that is by sharing one or more of their electrons. So for some of the time, one part of the molecule holds those electrons, and other time, other part of the molecule holds those electrons. So we see kind of this compromise where by sharing electrons, we get all parts of the molecule to that happy place, to that stable place. So let's have a look at these covalent bonds a little bit more. When we're sharing electrons between different atoms, we often illustrate this in our chemical shorthand by drawing that when we have two electrons that are being electron paired, that's being shared within the molecule, we draw a single line to symbolize that. If we want to do it a little bit better, a more accurate prescription, here we would see that sometimes the angles might be different because the molecule structure is not quite as two-dimensional as what we're seeing on our drawings. Sometimes we have two pairs of electrons that end up getting shared. So 4 electrons altogether. And in those instances, we draw 2 lines. Those 2 lines mean that we have 2 pairs of electrons that do get shared between these different parts of the molecule. So if these electrons are equally shared, and that means that they spend the equal amount of time at both parts of the molecule, we know these as nonpolar covalent bonds. Sometimes we also see that the electrons are shared unevenly. So they spend more time at one end or another end of a molecule. And we talk about now these electrons that are being shared, this covalent bond that's being formed, as being a polar covalent bond. So that was our covalent bonds, which was all about sharing. Ionic bonds are a little bit different. In ionic bonds, these different atoms are either gaining or losing electrons. As they're gaining or losing electrons, their net, the total number of charges, ends up being positive or negative. And we know that positive and negative net charges attract each other. So that's our ionic bond. Here's a good example of a reaction where we see that our first component wants to get rid of one electron, and as it gives it away to another element that's seeking to get an additional electron, we end up with the situation where both of these elements reach their happy state. However, as they're reaching their happy state, we're noticing that we are losing one electron from the electron shell here. So the number of positive charges at the nucleus is going to be greater than the number of negative charges thanks to the electrons. So the overall charge of this atom will be positive. Similarly, in this case, since we were gaining one additional electron, the number of positive charges in the nucleus is going to be less than the number of negative charges with the final outcome of the electrons. So the net charge of this atom is going to be negative. And we call these net charges that are positive as these atoms being cations, and atoms where we have net charges that are negative, we call them anions. And we end up seeing is that there's really an attraction between cations and anions. And this is what forms these salts that we often see in ionic bonds. And the final type of bond that I wanted to discuss is hydrogen bond. Hydrogen bond is not that different. It's just because water is so important for our life that we do kind of end up classifying this attraction of water molecules to other water molecules as a special type of bond, whereas I think that it's really not that different from what we've seen before. So let's unpack that a little bit. So in a single water molecule, we end up seeing that the electrons were shared unevenly between hydrogen and oxygen parts. Those electrons spend a little bit more time at the oxygen end than they spend at the hydrogen end. So the hydrogen end becomes just slightly positively charged, and the oxygen end becomes just slightly negatively charged. So the overall charge of the water molecule was neutral, but different parts of the water molecule have their differences in charges that we end up seeing there. And as a result, now that a single water molecule have different charges at different parts of them, when we put multiple water molecules together, we end up seeing that they're going to be interacting with other water molecules, forming these bonds between the ends that are negatively charged being attracted to the ends of other water molecules that are positively charged. And this is what we know as hydrogen bonds. And next thing that I wanted to talk about is a little bit about the fact, because we have this unique characteristics of water. This gives us a rise for properties of water that makes water particularly useful for us as a important characteristic for life. So water is a great solvent. Many things end up actually dissolving into water, and that's largely because of this polar nature of a single water molecule. So many things end up dissolving into water, and that becomes very useful for us when we study life. We also end up seeing that water has two forces, and the first force that I want to talk about are the cohesive forces of water molecules. Because water molecules are attracted to other water molecules, they form almost this kind of a bond between these all water molecules that allows us sometimes to go beyond what would otherwise happen. So cohesive forces describe how water molecules are attracted to other water molecules. And because of that, we can actually overfill a drinking glass over its rim without the water starting to flow out of the glass. It's those cohesive forces that are fighting to hold the water as a mass together or water as a whole unit together because we have those attractions between water molecules. So cohesion refers to the attraction of water molecules to other water molecules. Adhesion instead refers to the fact that water molecules are attracted also to other polar surfaces. And a good example of that would be, for example, morning mist on the surface of the plants or cobwebs if you wish, but we can use this for many purposes as well. So what we see in one classical chemistry class experiment is if we have a jar of water and we fill that with water and then we put a very, very thin glass rod in there, the water level will actually climb up in that glass rod. And the reason why the water level climbs up in that glass rod is because these water molecules inside are so attracted with these polar surfaces of this glass rod. So adhesive forces cause the water column to climb up on this glass rod tube. So unlike cohesive forces, adhesive forces were all about the attraction of water molecules to other polar surfaces. We actually end up seeing that because of these cohesive forces that we just talked about, water has a surface tension. And this surface tension can be highly useful for us. We see, for example, smaller bugs walking on the surface of the water because their weight is less than the cohesive forces. So their weight doesn't break the cohesive forces of the surface of water. But we would also see this if you've ever done jumping into the water and you've done a belly flop. Water can feel really hard to fall into. And that's because if you spread the surface area to a large surface when you're hitting the water, the cohesive forces will fight against breaking that surface tension and you will get that hard impact on your body. However, if you jump to the water with your toes or fingers first breaking the surface tension, it's going to be much less painful to do your jump into the water. Other thing that we end up seeing is that water is great at binding and releasing heat. So we end up seeing that a lot of life in the earth is concentrated on coastal areas or areas where we're close to bodies of water. And that is because these coastal areas really help us to even out the temperature changes throughout the day. So let's think of us here on this beautiful picture living by a coast of an ocean. So during the hot part of the day, the air and the environment on that coastal area isn't going to get as hot as we would expect because the big body of water will constantly keep binding some of that heat. So temperatures don't rise as high as we would assume otherwise. Then during night, when temperatures drop, the water will actually slowly start releasing the heat that has bound into it. So we end up evening out these temperature fluctuations on coastal areas by big bodies of water. This is not the case of what we're seeing here in Arizona a lot of the time because we have very little humidity and very little big bodies of water. We actually get drastic temperature changes between the day and night. As a result of that. So that's something to keep on mind. This doesn't have to be in this large of a scale though. We can transport heat from one body compartment to another body compartment thanks to moving fluids. For example, blood is largely made of water. So we use blood to transport heat from one body compartment to another. So another important property of water. We saw or kind of touched upon this. Water can take different forms: solid ice, liquid water, or water vapor, kind of the gaseous form. So that might be also important when we're looking at properties of water. And we see as water takes different forms, the volume that the same amount of water changes. What it takes changes. So for example, freezing a bottle of drink can be dangerous because as water freezes, it takes a larger volume simply because of the arrangement of those water molecules, and that can end up breaking that bottle of water compared to it being in a liquid state. Water works also as an excellent transport media. This really loops us back to the point that I said that water dissolves many things. So we can use water to transport materials, whether it's within human body, like I mentioned, blood, or whether it is in plants. We use water to transport the nutrients from the soil to the other parts of the plant. So water serves as a great transport media, which is again crucial for us as we study life. I also wanted to mention about the fact that we can talk about materials being either hydrophilic or hydrophobic. Hydrophilic materials are attracted to water, whereas hydrophobic materials avoid water. And again, this originates from this polar nature of a single water molecule. And this really gives us an explanation why we see on the cell membranes the phospholipids having both hydrophilic and hydrophobic portion. So the head of the phospholipid, a single phospholipid that we would see, it is hydrophilic, it's attracted to water, whereas the tail parts of the phospholipid are hydrophobic. They try to stay away from the water. And this causes these phospholipids to arrange spontaneously into two layers that make this membrane that's going to give us a rise to the cell membrane. So I think I kind of touched upon on this already. So we see that ice floats, and the reason why ice floats was because the same amount of water takes a larger volume when it's frozen versus when it's in a liquid arrangement. So that will cause that ice floats on liquid water. But that would also cause, for example, if you have a gardening hose that you leave out on a cold winter's night, what has been liquid water inside that gardening hose, as it freezes, it might take larger space, and as a result, it might actually rip that gardening hose and break it. So it becomes incapable of then when ice melts to hold that liquid inside because it's gotten damaged. Because as we're freezing the water, it ends up taking larger volume. So we're seeing that liquid water is relatively dense, whereas ice water in a solid state water, that's lighter, and that's why the ice tends to float on the surface of water. I also wanted to mention quickly the pH scale. The pH scale tells us the concentration of hydrogen ions in a solution. So we have a pH scale where 7 is typically the neutral, but if we have higher numbers, we see that there's little hydrogen ions present, and these are known as basic substances. And if we have lots more hydrogen ions present than 7, at 7, the number is going to be lower for pH scale, and we call these as acidic solutions. So that's something to keep on mind. Well, we also saw in your introductory biology classes buffers. Buffers are chemicals that keep the pH range within a normal range. So they bind into materials that would otherwise change the pH of a solution and neutralize them. By doing so, keeping our pH in a constant range. I also wanted to talk a little bit about a specific field of chemistry, which is going to be our organic chemistry. And we can really classify things in life as being living or non-living. So living things are either currently living or have origin that they came from living organisms, whereas non-living things like rocks, they've never been living. And organic chemistry is all about looking at these structures, these materials that have been living. And organic chemistry is based on carbon and hydrogen. And the reason for that is that carbon has 4 electrons on its outermost shell, so on its valence shell, which makes it very reactive. So carbon atoms typically tend to react well in chemical reactions. And what they do often end up doing is that they bind to hydrogen atoms where we have an easy way of, if we have 4 hydrogens binding into 1 carbon, forming a molecule where all of those elements get that happy state of having full valence shell by sharing some of the electrons. So we end up seeing that most organic materials are built on hydrocarbon backbone of chemistry. And what we're seeing here is some examples of those hydrocarbon backbones. And what we're actually seeing is that we have the same number of carbon atoms on all of these schematic representations that we're seeing on the screen. However, the arrangement is very different. So when we have the same chemical formula, but it takes a different shape as a molecule, we're talking about isomers. And in addition, when we're looking at organic chemistry, what we want to pay attention is not just the hydrocarbon backbone of the molecule, but we want to pay attention to the functional groups. So these are groups of molecules that always have a very similar effect on how the molecule behaves, for example. And I've provided this list of functional groups for you on your Canvas course. You, I believe, have also that on your textbook materials. So that might be a nice resource if you're looking more into that. I want to take us away from the chemistry and now focus on molecules. As we defined earlier on, molecules were when we had two or more atoms that were held together by chemical bonds, and typically molecules ended up being chemically neutral. Well, we actually have what we know as macromolecules. These are especially large molecules, and there's 4 macromolecules that form the basis of all life. And these are going to be our carbohydrates, lipids, proteins, and nucleic acids. And on this chapter, we had a look of each of these macromolecules, kind of going through a little bit about them and how that relates to life. So let's start with our carbohydrates. But before we do, I want to make sure that we're clear of some of the terminology. When I'm talking about a monomer, that's just single unit of matter. When we have polymer, we have multiple units that then have joined together. And this is going to be important for us. I also want to talk about a few processes, and the first of these is what's known as a dehydration synthesis. So let's unpack a little bit what's happening in dehydration synthesis. The first word that I want us to focus is the part synthesis. So in this reaction, we're taking individual elements, so we're taking monomers, and we're forming a larger element out of those monomers. So we're forming a polymer out of monomers. So that's what I mean by the part synthesis. What the dehydration refers to is that as part of this reaction, we are actually producing water. So as we are having these monomers joined together to form a polymer, some water is being released as a byproduct of this reaction. So I hope that that helps to kind of unpack that term a little bit. The opposite reaction of this would be what we know as hydrolysis. In hydrolysis, we have a polymer that's breaking apart into multiple monomers. But in order for us to do this reaction, we need water to do so. So the part lysis refers to the fact that we take a polymer and we break it into monomers. And the hydro part tells us that in order for us to do that, we need to add water to this reaction. So hydrolysis, taking a polymer, breaking it apart into monomers in order to do this, we need water to help us in this reaction. So we see this, for example, really this interplay of dehydration synthesis and hydrolysis when we have things that we dissolve into water, and then if we kind of distill that water away and or just let the water evaporate, the material that has been dissolved into water might again crystallize, forming, for example, salts. In this example, I have sugar cubes that either can dissolve into water or can crystallize as the water gets removed from the reaction. I also wanted to talk about a concept of an enzyme. So enzymes are things that assist us in reaction. And often there's a misconception amongst students and amongst even textbooks how they're written that all enzymes would be catalysts. Catalysts are enzymes that speed up reactions. But that assisting part can be much more than just speeding up. It can be that we make the reaction easier to take place, so we lower the activation threshold. It can be that we make the reaction more efficient, or somehow in other ways add a beneficial characteristic to that reaction. A lot of the time, the enzymes are working by making these reactions faster. So I wanted us to look a little bit about the structure of an enzyme. And that's what we're seeing on this series of pictures. So here we have on yellow an enzyme, and the green part is the molecule that the enzyme is acting on. So the molecule will bind into an enzyme, to the enzyme's active site. The enzyme might actually change its shape while it's working on that molecule. And once the job has been done, so in this reaction, we were breaking this larger molecule into smaller particles, the enzyme returns back to its original state and can be reused. So this reaction of going from a larger molecule into smaller, this would have happened anyways, but with the help of an enzyme, we were, for example, able to speed up this reaction. So that's what I'm talking about when I'm talking about enzymes. And as I mentioned, many enzymes are catalysts, so they speed up chemical reactions, but it doesn't mean by any means that all enzymes would be catalysts. So only some. So now we're ready to talk about these biological macromolecules, and let's unpack those a little bit, starting with the carbohydrates. So carbohydrates, often when I ask from my students what they are, they think of things like bread, potato, corn, rice, pasta, all that lovely things to eat. But we end up finding carbohydrates also in many vegetables, many green plants. So there's many types of carbs that we can get from diet. And carbohydrates, by large, are used as a source of energy and raw materials that we can use to build different parts of the body, for example. And this is really why we are so attracted to eating carbohydrates. It gives us that feeling of, oh, I'm getting good energy. And this is really what I would speculate as an evolutionary remnant from the time when energy and nutrients and sources of food were in short supply. So we are, as a humankind, attracted to those high carb food products. So we end up feeling that, oh, I'm feeling good. I'm getting all the carbs I need. I do want to remind you that we do need also, in addition to things that we utilize in our body, either as a raw materials or energy, we need to have food that's non-digestible. And would be our dietary fiber. Dietary fiber serves a few different purposes. First of all, it adds bulk to the stuff that we eat. So we end up feeling full because we've now eaten enough. If you don't have any fiber in your diet, you often might end up feeling hungry all the time. But having high fiber diet gives you that sense of being full thanks to the physical stretch of the stomach, for example. So the stomach is literally full. Other thing that fiber does, fiber helps us to push material along the digestive tract or digestive system. So it kind of helps us to also keep the pathway moving and clear materials along it. Not all carbs are same. We can have carbs that are very simple, so either monosaccharides or disaccharides. These are simple sugars. And we can have carbs that are very complex, polysaccharides, so they're made of multiple subunits. As you are consuming carbohydrates as a source of energy, you're breaking polysaccharides into monosaccharides. So that's how eating, for example, whole wheat bread is better for you because it's going to stick around in your body and you can slowly break down those complex carbs into smaller, because it's only these smaller carbs that we use as a source of energy. So that's why eating these complex carbs, it keeps the carbs around in your body for a longer time. However, if you eat really simple carbs, those are sugars that are easily available and quickly available for you, and you get that burst of energy, but that energy is used really quickly. I also wanted to mention in terms of carbohydrates, a polysaccharide, chitin. Chitin is found, for example, in exoskeletons of many animals that we look at, such as cockroaches. It's rather than having internal skeleton like we humans have, Many bugs do have an exoskeleton, so their skeleton is around their body that's made of chitin. And I often compare that in my class to students, like thinking of the armor of a medieval knight. We do, of course, use bug sprays. Many bug sprays end up dissolving that chitin exoskeleton of an animal. I often think about that what a way to go. Your skeleton is literally disappearing and you die as a result of that. Like I mentioned, eating more complex carbs is considered better than eating simple carbs because those complex carbs remain around available for your body for longer, whereas with simple carbs, simple sugars, you get that spike of energy and then we burn it off and we're done with it. The second group of biological macromolecules that I wanted to talk about is going to be our lipids. Our lipids, again, when I ask from students, where would you get fats in your diet? I hear cheese, butter, lard, ice cream, oil, all these tasty things. But you can also get lipids from more healthier dietary choices, such as avocado, fish, nuts, and seeds, olive oils, things like that. Lipids are a very, very, very concentrated long-term energy storage, so much more than carbs. And again, I think that this is why we're attracted to eating fatty foods, because evolutionarily, we were always wanting to make sure that we get as much resources when they were available as possible. So eating fatty things gave us a great source of energy for later uses. Other thing that we see with the lipids is that they are insoluble in water, so we often end up seeing those being used to form protective layers in the body. For example, a lot of aquatic animals that we see might have a lipid layer on top of their fur, and even we end up seeing that plants may have a lipid layer protecting their leaves, forming this barrier, keeping inside and outside separate. When we're talking about lipids, I want to talk a little bit about triglycerides. Triglycerides are made of different elements, and what the elements that I want to highlight is that we have one glycerol and 3 fatty acid chains that attach to that glycerol to form a single triglyceride. This, of course, gives us a rise that we can, through the process of hydrolysis, break down a triglyceride into glycerol and 3 fatty acid chains. Or we can put 3 fatty acid chains and 1 glycerol together by dehydration synthesis process to form a triglyceride. So kind of applying a little bit what we learned about the terminology. I want to shift our focus on a single fatty acid chain, and let's talk about those a little bit more. So what we're seeing is that not all fatty acid chains are the same. Some are what are known as saturated fatty acids. In these saturated fatty acids, every single carbon is joined to the next carbon by a single bond. These are things, food sources that we typically end up seeing fats that are solid in a room temperature, such as butter or lard, and they are known to have a higher risk and higher contribution to cardiovascular disease, so they are considered less healthy option of these fatty acid types. Unsaturated fatty acids instead have at least one, if not more, double bond in their structure, and this causes a kink in the structure of that fatty acid. These unsaturated fatty acid containing materials are sources of fats in our diet that are liquid in room temperature, such as oil, for example, and they are considered as a healthier option for our consumption. We have tried by making these man-made healthier options by producing something that's known as trans fats or hydrogenated fats. Here we use industrial processes to add hydrogen to liquid vegetable oils to make them solid. So we're chemically altering liquid fats to make them solid in a room temperature, and the idea was to find kind of a healthier option of consuming fats and healthier fats that still can be used as traditional fats that are solid in a room temperature. There is some debate about this, and we're seeing that these trans fats or hydrogenated fats do have negative health outcomes, for example, with the buildup on the artery walls and so on. So we don't really recommend that as largely anymore. Those were a big fad earlier on in the history when we didn't yet know really. We thought that trans fats were, and consuming trans fats were the health choice to do, and now we're kind of backtracking a little bit out of that. The manufacturing process of margarine is a good example of that. Again, thought to provide us a healthy option, but we end up seeing that not necessarily so. The production process of margarine, you can study that from this slide yourself independently, but there's some things that are a little concerning. For example, we use heavy metals, we bleach the resulting product. So I'm a little hesitant about whether margarine production is really giving us the healthy option that we thought we would get. Well, when talking about lipids, we obviously need to talk about phospholipids as well. Phospholipids are what gives us our cells' cell membranes. So let's explore that a little bit. So here we have a single phospholipid. You remember it had a hydrophobic head part and hydrophilic head part that was attracted to water, and hydrophobic tail part that tried to stay away from water. And that caused these phospholipids to spontaneously arrange in a manner that formed a phospholipid bilayer, 2 layers of phospholipids, and those were what our cell membranes were made of. So that's going to be really important when we look at the cell structure. Then we can also, when we talk about lipids, we end up seeing that steroids are important, for example, in our endocrine system, testosterone, estrogen, progesterone, for example. And these are hormones that are made from these ring-like structure, 4-ring-like structured arrangements of fatty material. Now I want to talk a little bit about proteins. One of the things with proteins is that proteins are the building material that, for example, muscles are built. They are often very, very important in our diet because proteins and dietary proteins are not stored. They don't stick around in our body. So you need to consume proteins in your diet if you're, for example, working out and trying to build up muscle mass. Good sources of proteins would include, for example, milk, eggs, especially the egg whites, beans, meat, tofu. And that's why you end up seeing sometimes people at the gym who are drinking or getting supplementary protein powder to provide that structural protein for when they're trying to build that muscle mass. Because what happens if you don't have carbs and you don't have lipids as a source of energy, body will start using proteins as a source of energy. So technically you could be trying to build up muscles but burn your old muscles to build new muscles, so which would not be very good outcome for us. So like I said, in gym you often see people who are consuming those protein supplements to ensure that they're getting that muscle growth. I mentioned that if you just keep exercising, you don't get sufficient amount of protein from your diet, and there's no carbs, there's no lipids in your body to use as a source of energy. Your body will start burning off muscles as a source of energy. But we use proteins for many other things as well. We use them to support body structures, but also physiologically. They play an important role in metabolism, transporting materials, defense, regulation, creating motion through the skeletal muscles. An important role of proteins on building those as well. Proteins are polymers of amino acids. So here you see that on the screen, and the R would be the functional group that could be varied. And again, you do have that handout of various different kinds of functional groups for you to study. And I think that that's the handout that I'm referring to. So what I wanted to do with this slide was to highlight that proteins can be studied at many different levels of detail, and we can do a chemical representation of what molecules are forming or what atoms are forming. a protein. We can do kind of more two-dimensional sheet-like representation of that, or we can do a fully three-dimensional kind of molecule structure of that. That's often illustrated on a computer as this three-dimensional blob that you can rotate, and so on and so on. So protein can be studied at different levels. One thing is that we notice, though, is that as we're changing a protein structure, the shape of the resulting molecule changes as well. So example that I have on the screen, Nicole Kidman back in the day had straight hair, but when she took a perm, she was changing the protein structure. So hair is made of protein, and that chemical change caused the hair shape, the resulting molecule shape, to change as well from straight hair to curled up hair. So that's what I want to emphasize when I say that the chemistry has an impact on the folding of a protein. We see this in clinical setting as well. We have our red blood cells that should fold nicely to these biconcave discs, but sometimes we can have errors there and we end up with sickled red blood cells. And you'll get to learn a lot more about those if you take 201 or 202 with me later on. We'll talk about sickle cell disease in greater detail when we talk about blood as a component of the course material that we cover. So like I said earlier on, we use carbs, lipids, and proteins as source of energy in our body. And what we end up seeing is that it really is to do with what's available. If carbs are available in your body or to use as a source of building materials, those are what we end up using. If there's no carbs, we end up using fat, body fat, as a source of energy. So this is where many of these non-carb diets are based on, with the idea that, well, if you don't have carbs in your body, well, maybe, and you exercise, you need source of energy, maybe you start burning off the body fat. Well, the danger with these diets is that if you don't have enough fats either, then you will end up start burning off proteins, so muscles from your body, for example. So again, that is the explanation of what's the availability, what body prefers to use as a source of energy, and we build from that. The final group that I want to mention is going to be our nucleic acids, and we'll talk a lot more about those later on the course, so I don't dwell on those at this point as much. But with nucleic acids, I'm talking, of course, of our DNA and RNA. DNA is what we store the genetic information as, and RNA plays an important role as we use the genetic information and convert it into a protein. And protein was a chain of amino acids that then folds and takes a shape. So for that process, we have RNA. Here we have a single nucleotide that makes up the DNA. We see that it's made of sugar and phosphate groups. Let's see if I can get my pointer out. So our sugar and phosphate group. Then we have a varied group that can be either adenine, guanine, cytosine, or thymine. And these are the bases that we see on the DNA. So if we go back to the previous slides, the backbone of the DNA strand is made of that sugar-phosphate structure, and those bases are these horizontal steps, if you wish, that then bind with each other. And obviously you remember that in case of RNA, the thymine was replaced by uracil, adding a little bit more complexity there if we're doing decoding. The final thing that I want to talk about is going back to what we've seen before, looking at the levels of organization and focusing on the cells, because cells were the fundamental basic unit of life. They were the smallest unit of life that we studied. Cells are relatively small normally, so we can study, we can see some elements of the cell with light microscopy, so we can see the cell membrane, we can see the cell cytoplasm and nucleus. But really to study cell organelles in greater detail, we do need to use electron microscopy, and that's a little more complex technique and not available in every lab, especially at our lab. So there I have the diagram that I've shown you before about the scale of various different things. and we end up seeing that cells are very small typically. And that's because we want to have optimal surface area to volume ratio. So if we had a really large cell, we wouldn't have enough surface area for that cell in comparison to the volume of that cell, and supporting that cell would become very difficult. I often describe this to my students as consider that if you would have a gas tanker, if the size of the gas tanker grows too big, or one of those gas trucks that drives on the highways, you're going to end up using more gas to move that gas. So you want to keep it at the size where you're actually transporting gas and not using all the gas just to transport the gas. So we're wanting to keep the distances within the cell manageable. So that's why most cells are small in size. I think I used this same slide last week when we discussed about the cytology being study of cells and histology study of tissues. So when we have multiple cells on the same area working for the same purpose, they form a tissue. Sometimes I get students asking when we're looking at cell organelles and parts that make up a cell, that how did it come about? Well, our understanding at the moment is that the first cells that became multiple cell organelles were a result of accidental symbiosis between a cell and an organism that entered inside there, and it ended up being mutually beneficial, so they remained there. When we're studying at cells, we can study cells at a few different scales. We can talk about prokaryotes and we can talk about eukaryotes. Prokaryotes were first to evolve in the history of life. They're much simpler, smaller, typically single-celled organisms. They are not complex cells, so there's no cell membrane-bound nucleus inside prokaryotes. Instead, the DNA is just floating free within the cytoplasm. You don't end up seeing a lot of cell organelles in prokaryotes either. You can see a few structures, but it's relatively simple and, like I said, small cell. Eukaryotes are complex, larger cells. They emerged later in the evolution of life, and within eukaryotes we see distinct, separate, specific compartments for cell organelles and functions of the cell. And especially importantly, the DNA is housed inside the nucleus. So when we study about cells in this course, we often talk about the eukaryotic cells, because eukaryotic cells are what we see, for example, human body made of. This specific compartments nature of eukaryotic cells is going to be important for us as we move on to studying the different parts that make up a cell. So the first part that I've already kind of touched upon on a few occasions is the fact that cells do have cell membranes that forms the outer boundary of the cell, and those were made of our phospholipid bilayer, so 2 layers of phospholipids. So that's the cell membrane. So like I mentioned, we see here a single phospholipid, and then there's going to be different parts of the phospholipid. We see that phospholipid is made of a phosphate portion, glycerol portion, and then those fatty acid chains. So that really gives us an explanation why the name phospholipid. When we end up seeing the bilayer, I'm referring that there's 2 layers of these phospholipids. And you remember that the head part was hydrophilic, attracted to water, whereas the tail part was hydrophobic, avoiding water. And this causes the spontaneous arrangement of 2 layers, with the tail staying away from the water, folding inside against each other, whereas the head parts were attracted to water, facing outside. Within cell membranes, we can also see proteins embedded in there. And proteins can serve many different purposes. They can be channels for passageways of materials. They can actually move materials intentionally as transporter pumps. They can play important in recognizing, for example, other cells or other parts of the body. They can work as receptors for many things. So there's a key and lock mechanism then that we're going to talk about. They can serve as enzymes that we talked about a little bit earlier on, assisting in chemical reactions, or they can form junctions from one cell to another for passage of materials. When we talk about cell membranes, we often describe cell membranes as being a fluid mosaic. What I mean by that is that they're very constantly changing, moving structures, and they're made of multiple different components. So these diagrams present you an overly simplified view of what's going on with cell membranes. So phospholipid bilayer plasma membrane can also have adaptations. Not all cell membranes are flat. There can be folds, there can be villi, microvilli, and these are often used to increase the surface area of the cell. So the surface area was important for movement of materials in and out of the cells. Let's have a look of what's inside the cell, and this is going to be our cytoplasm. This is kind of a jelly-like liquid, mainly water, also some other materials that fills really the rest of the cell and provides in that sense a way for us to have that cell full and nice shaped space for the materials to be there. We also have an important cell organelle, which is going to be our nucleus. So nucleus is where we're storing the genetic material, we're storing the DNA. And what we see is that often the DNA is wrapped around proteins and forms this kind of condensed shape in certain stages of the cell cycle. And the reason why DNA was so important is that sections of DNA are known as genes, and they give us instructions how to produce different kinds of proteins. Within the nucleus, we can see on that nuclear envelope that there are small holes that allow materials to move in and out in a controlled manner. And remember that DNA always stayed inside the nucleus. We can make a copy of the DNA, and the process of making a copy of the DNA and producing a messenger RNA is known as a process of transcription. I talk to my students, think of when someone's transcribing. In old days, you might have a secretary who was transcribing what their boss was telling them. So it's making a copy of the information. It's not taking the actual information, it's just taking a copy of that. And then that, even though DNA could not leave the nucleus, that mRNA copy can leave the nucleus, and it can be brought to ribosomes. And ribosomes are used to translate the information from that mRNA with the help of transfer RNA to proteins. So we're making an amino acid chain that then can fold into a protein that is taking that information from the RNA and making something useful, in this case the protein, out of that. And that process is known as translation. So I hope that helps with some of the reminding you of basic concepts that you've seen before. A few other cell organelles that I wanted to mention. Mitochondria, that's often described as a powerhouse of the cell producing ATP. We actually end up seeing that there are other parts of the cell that also can produce ATP, but not in as great quantities. And these folds within the mitochondria are known as cristae. Interestingly, the mitochondria has its own maternal DNA, and we end up finding ribosomes there as well. So other things that we would see in cells, we only see in plant cells chloroplasts. Chloroplasts are the site where photosynthesis takes place. So we convert solar energy and CO2 into sugars. We make sugars and produce oxygen as a byproduct in the process of photosynthesis. And again, you can learn a little bit more about different parts of the chloroplasts as you study the lecture material. We'll also end up seeing endoplasmic reticulum, often abbreviated as ER, in the cells. These are networks of membranous tubes within the cell cytoplasm. And there's two types of ER. There's a smooth ER that has a nice smooth surface. There's no ribosomes attached to that surface. And then there's something known as rough ER, where we end up seeing on that ER surface ribosomes attached there, and that gives it kind of a bumpy appearance. And it's the ribosomes that were responsible for production of proteins. So that helps us to, again, figure out where that protein production process takes place. Some other things that we can see in the cell, we can see Golgi apparatus. This is a kind of stacked set of membranes that have folded and serves kind of as a space where we're receiving material, sorting, repackaging it, and sending it out to other parts of the cell. I often give my students an analog that it's almost like a distribution center of a trucking company. It receives, it sorts, repacks, and sends out materials from one part of the cell to other parts of the cell. Then we might have various different sacs within the cells. These can be our vesicles, lysosomes, and vacuoles, either holding materials, transporting materials, things like that. In cell, I wanted to mention also centrioles. These are a pair of cylindrical tubes near the nucleus, and they play an important role during the cell division process as we form the spindle that you learned about in your BIO201 class, I'm sure. Cytoskeleton is really the microscopic filament and tubule structure within the cytoplasm that gives the cell its structure, its shape. It provides kind of a scaffolding for the cell. It also serves an important role as kind of providing movement pathways for moving materials within the cell. And of course, we want to draw a distinction between animal cells and plant cells. We already saw one difference, which was that presence of chloroplasts in plant cells, so they could produce sugars through the process of photosynthesis. Other differences to notice is that in plant cells, in addition to the cell membrane, we have a cellulose wall that gives plant cells this kind of very strong shape of the cells and allows us to pack up those cells on top of each other and form these strong structures, whereas animal cells don't have that cellulose wall. They are just soft-walled structures. Cells can join together in many ways as well. We can have tight junctions, distal zones, or adhesion junctions, and also gap junctions. This can be to hold cells together or move materials from one cell to another. I normally talk with my students about catabolism and anabolism as reactions as well. You can check those from your lecture videos. And I talk about the process of endocytosis and exocytosis, so taking things into the cell with the help of cell membrane or eliminating things from the cell with the help of cell membrane. And at this point, I think we've spent a rather long session together, so I'm going to call it quits at this point. We won't look at the actual assignments this time around. I'm happy to do it at the later live online session if that's helpful for you. I hope that this nutshell review of key concepts has been helpful. Remember, full lecture material available on Canvas. And like I said, even though this might seem like a lot of material, this is really revision for us of the things that we've covered before. So we're ready to dive into that process of learning about human A and B, since we're all at the same place with the basic concepts. So, like I said, it's been a busy session for us, for sure, but I think it's been a useful session. I appreciate anyone who joined me even later on through a recording. And as always, I look forward to seeing you on those discussion forums, seeing your work being submitted, interacting with you. This is very much a course where I want to be a support and a resource for you. So don't hesitate to let me know if you have questions that come up. I hope you have a very good week, and I look forward to seeing the great work taking place on this course. For now, that's it for this session. Thank you and bye.